Hi guys, welcome to our next video, and today we're going to be having a look at what is light and how it relates to slits and wave phenomena. So firstly, what is light? Now light is energy, and energy comes from atoms, and basically as an atom absorbs energy, electrons will jump to a higher energy level, and when they go back to their normal energy level, they release that extra energy as little packets that move away from the atom, and these are called photons. Now basically these photons are what we see as light. Now light is basically a stream of photons. So the photons, are what we can also know them as, is a transverse wave. So light is made up of a transverse wave, and basically the way that it looks is we've got two little waves, one going in one direction and the other one going at right angles, and one of them is the electric field of the photon and the other one is the magnetic field of the photon. So basically we've got, and that's why it's called an electromagnetic wave. So half of it is electric and the other half is magnetic. Now the energy is perpendicular to the motion of the particle. So it's the moving photon that creates the electric and magnetic field, and light has both an electric field and a magnetic field, and they're at right angles to each other. So half of it is electric field and half of it is the magnetic field, and they're both made up of transverse waves. So basically light is a combination of two transverse waves. So some properties about light is that its speed in a vacuum is 300,000 kilometers per second, or if we're going to look at it in miles, some questions, if we're looking at an American textbook, might have them in miles, and its speed in other materials is generally slower than in air or in a vacuum. So air is slower than in a vacuum, and water is slower than in a vacuum, and again, so is glass. So they slow down depending on the material. Okay, so here we have the electromagnetic spectrum, and this is basically a way to compare the wavelengths of electromagnetic radiation, of which light is a kind. So here we have what we would normally see as light, which is our visible light. You can see it's only a tiny, tiny amount of the electromagnetic spectrum. As we get bigger, we've got longer wavelengths. Here we've got some infrared is the next one down with a longer wavelength, followed by microwave, and then radio waves are common sources of these. AM radio is really long radio wave, then we have FM radio, microwave ovens, then we get radar, and here we have light bulbs, which we can see, so that's in our visible range. And up this end we get shorter wavelengths, so as it starts getting smaller, we've got the electromagnetic radiation becomes higher energy. So we have X-rays, gamma rays are more energetic than, say, our visible light waves. So generally we see here the wavelengths are measured in meters, but they also appear in questions quite commonly in a unit called nanometers, which is times 10 to the negative 9 meters. So we'll have a look at how to convert that as well. Okay, so the visible spectrum that we can see, it's the same thing that we use to remember a rainbow order is Roy G. Biv, because that is also the order of which it appears in the electromagnetic radiation spectrum. Oh my goodness, here we go. So here we've got infrared light, and then the first part of the visible spectrum is our red, for our Roy, at 700 nanometers, and then it becomes orange, yellow, green, blue, indigo, and violet. And heading down the next thing along is our ultraviolet, which we can't see. So visible light is, from about 700 nanometers down to about 350-ish nanometers. So the electromagnetic spectrum, most of the spectrum is actually invisible to us as humans. So down the longest end, the longest wavelength, we have radio waves, which is really useful in radio and TV broadcasting. If we go back the other end of the scale, down the really, really short wavelength end, we have X-rays and gamma rays and things that we can use in medical research and things like that. Now, it's a common thing to basically debate about whether or not light is a particle or a wave. And there's two different models of thought here, and basically we've got the wave model of light, which explains most properties of light and explains how it interacts and things like that. And then there's also what's called the particle theory of light, which is basically saying that light behaves as a stream of particles, which is where we get the idea of photons. Now, it's actually a bit of a combination of these things. It sometimes acts as a wave and it sometimes acts as a particle, but for our purposes right now, we are going to assume that light is a wave. All right, that way we can look at its interactions in a little bit more clarity. Next year, you'll cover it in a lot more detail, why it behaves as a particle and why it behaves as a wave. We're going to have a look at now diffraction and interference of light when it's behaving as a wave. So diffraction is when waves spread out from the edge of a gap, and we've had a look at this already. So if it goes through a gap, we can see it bend, and the same thing happens, and the more closely related the wavelength of the wave and the size of the gap, it's going to bend more. So if it's really similar, we'll get more diffraction. The other thing that can happen over here is that the more diffraction is achieved, so the more the wavelength, more diffraction if the wavelength is increased or the frequency is decreased. So if it's got a high frequency here, it's less likely to diffract. If it has a low frequency, it's more likely to diffract. Okay, so how does this work? We're going to have a look at what happens if we pass it through this gap. So if we put a light wave through a small opening, or what's called a slit, it creates an interference pattern. So here we pass it through our wave, a little gap. We start to see the bouncing effect of an interference of this diffraction that happens because it goes through the gap. Now, if the slit is about the same size as the wavelength, we'll get maximum diffraction. And some parts will interfere constructively and they'll add together, and other parts will interfere destructively and they'll cause periods, like parts of cancellation almost. And what we get if we put up a screen here where the light was falling, we'd have parts that were really bright, which would be the constructive interference, and we'd have parts that were quite dark or black, and that would be negative interference. So we call these maxima and minima. Now obviously a maxima is a bright part and a minima is a dark part. So we can work it out as a bit of a formula, and we'll have a look at that in a bit more detail later on. But if we were to actually map out the intensity of the light falling on this screen over here, in the middle you can see here it's quite bright, so we've got the intensity of the light is quite high, and then it slowly has periods over here of darkness and then brightness, darkness, brightness, and it maps that out here on the screen here. So there's a couple of useful points on here. This is talking about the gap between the slits, and here in L, capital L, is how far away the screen is, and there's a couple more, and this one lambda is the angle of the part we're looking at, whether it's a maxima or a minima, but again we'll have a bit of a look at that in a moment. Now single slits produce a bright bit in the middle, and that's called our central maxima, and then it'll have other maxima on either side, which will be bright ones or dark ones. It's our minima maxima equation. We'll have a look at that most likely next year, but it's there if you'd like to have a look. Okay, now this is more interesting. We're going to look at a double slit diffraction. Now, in 1801, Thomas Young proved that light is a wave by creating an interference pattern for light passing through two small slits. And this was the experiment that he set up, and basically he had one screen to have just one set of wavelengths coming out the second screen, and then he had two little holes or slits in the second screen. And you can see here, but because of the diffraction of the two waves coming through these slits, we have definite portions here of constructive interference and some of destructive interference. And here's his screen, and this is a maximum, minimum, maximum, minimum. So where it says minimum, it's going to be a dark patch, and where it has maximum, it would be a light patch. Now in the experiment, it goes through the first screen and then the second screen, And again, we get these, if this is the fringe pattern we get, in the middle we get a central fringe, and then we get ones either side. So again, we've got here, you can see them quite clearly, a dark spot, a light spot, a dark spot as we move away. Now double slits produce the same sort of a pattern, but with less intensity in the middle. And the equations for maximum minimum are all the same for all interference patterns, but again, we'll have a look at that in a bit more detail later. The only thing we need to know for our experiments that we'll be doing is one of Young's double slit equations, and this one's saying that delta y, or the difference in y, is equal to the wavelength divided by d with a capital L. Now, what are these? Well, we know this one. We know that this is the wavelength, and this is referring to the wavelength of the light that we're using, that we're actually shining on our screen. Now, delta y is talking about the distance between the fringes, so how far away these fringes are from each other. Other parts you might need to know is d. Now, d is the distance between our two slits, and over here we can see it's measured in meters. And if we need to know L, that will be the length away from the screen, or how far away the distance the screen is from the slits. And other things you might want to know is n. If you had a look at the other formula from before, n is which number of order of maxima it was, so whether it was the first one, the second one, third one. They might come up as well in a couple of equations. Now, basically, things to look for: make sure you know what part you're working for this equation, and maybe write down the parts that you know, or the parts that you're given in the question before you start, and that way you know if you have to rearrange your equation, which part you have to try and make your subject. So for this one, this equation is giving us, this is the distance between the fringes, can be found by knowing this information. Now, if we were asked to find the distance between the fringes, we would then have to, or if we were asked to find, say, the wavelength, we would have to rearrange and make the wavelength the subject. So we need to be really confident with our rearranging skills. Now, we'll have a bit of a practicing class about how to rearrange this formula, and also how to convert into making sure that we've got the right unit of our measurement. So in the questions, as I said before, wavelength is very commonly given in a unit called nanometers, which is times 10 to the -9 meters. But before you can use nanometers in your formula, it must be converted to meters. And the same thing with your distance between the slits. So this is normally given in millimeters, and as is this distance here, normally given in millimeters. So it's really, really important that you convert everything into the right units first, and then that you have the right subject for your equation before you can start popping your measurements in and utilising it properly. All right, we'll have a look at more questions in class.